Types of noise. Analog signals processed by integrated circuits are corrupted by two different types of noise: device electronic noise and environmental noise. The latter refers to seemingly random disturbances that a circuit experiences through the supply or ground lines or through the substrate. We focus on device electronic noise here and refer the study of environmental noise. Thermal noise. Resistor thermal noise. The random motion of electrons in a conductor introduces fluctuations in the voltage measured across the conductor even if the average current is zero. Thus, the spectrum is thermal noise and is proportional to the absolute temperature. Noiseless resistor are Vn square SVF 4kTr, thermal noise of a resistor. As shown in figure, the thermal noise of a resistor R can be modeled by a voltage source followed by a voltage source with one-sided spectral density SVF equal to 4kTr, F greater than equal to 0, where K equal to 1.38 into 10 to the power minus 23 Jk is the Boltzmann constant. Note that SVF is expressed in V square Hertz, thus we write Vn square equal to 4 kTr, where the overline indicates averaging. We may even say the noise voltage is given by 4 kTr even though this quality is in fact the noise voltage squared. For example, a 50 ohm resistor held at T equal to 300 K exhibits 8.28 into 10 to the power 19 volts per hertz of thermal noise. To convert this number to a more familiar voltage quantity, we take the square root, obtaining 0.91 n volt root over hertz, while the square root of hertz may appear strange. It is helpful to remember that 0.91 n volts hertz has root hertz has little significance per se and simply means that the power in a 1 volt bandwidth is equal to 0.91 into 10 to the power minus 9 square volts. The equation SVF equal to 4 kTr suggests the thermal noise is white. In reality, SVF is flat 4 up and roughly 100 terahertz, dropping at high frequency. For our purposes, the white spectrum is quite accurate. Since noise is a random quantity, the polarity used for the voltage source in figure is unimportant. Nevertheless, once a polarity is chosen, it must be retained throughout the analysis of the circuit. Throughout the analysis of circuit, so as to obtain consistent results. The thermal noise of a resistor can be represented by a parallel current source as well. Figure 4. The representations of figures to be equivalent. We have Vn square bar by R square equal to In square bar, that is In square bar equal to 4k T by R. Note that In square bar is expressed in A square by Hertz depending on the circuit topology. One model may lead to simpler calculation than the other. Noiseless resistor are In square representation of resistor thermal noise by a current source. The dependence of thermal noise and some other types of noise upon T suggests that low temperature operation can decrease the noise in analog circuits. The approach becomes more attractive with the observation that the mobility charge carriers in MOS devices increases at low temperatures. Nevertheless, the required cooling equipment limits the particularity of low temperature circuits. MOSFETs, MOS transistors, and also exhibit thermal noise. The most significant source is the noise generated in the channel. It can be proved that for long channel MOS devices operating in saturation, the channel noise can be modeled by a current source connected between the drain and source terminals with a spectral density In square bar equal to 4kT gamma gm. In square equal to 4kT gamma gm. Thermal noise of a MOSFET. The coefficient gamma, not to be confused with the body effect coefficient, is derived to be equivalent to 2/3 for long channel transistors and may need to be replaced by larger value for submicron MOSFETs. For example, gamma is about 2.5 in some 0.25 new meter MOS devices. It also varies to some extent with drain source voltage. The theoretical termination of gamma is still under active research. The ohmic sections of a MOSFET also contribute thermal noise, as conceptually illustrated in the top view of figure A. The gate, source, and drain materials exhibit finite resistivity, thereby introducing noise. For a relatively wide transistor, the source and drain resistance is typically negligible, whereas gate distributed resistance may become noticeable. In the noise model of figure B, a lump resistor R1 represents distributed gate resistance, viewing the overall transistors as distributed resistors shown in figure C. Layout of a MOSFET indicating thermal resistances. B. Circuit model. C. Distributed 8 resistance. We observe that the unit transistors near the left hand see the noise of only a fraction of Rg, whereas those near the right hand see noise of most of Rg. We therefore expect the lump resistors in the noise model to be less than Rg. In fact, it can be proved that R1 equal to Rg by 3 while the thermal noise generated in channel is controlled by only the transconductance of the device. The effect of RG can be reduced by proper layout shown in figure. In figure are two examples. In figure A, the gate is contacted by both ends, and in figure B, the device is folded. Each technique reducing RG by a factor of 4 will hereafter neglect the thermal noise due to the ohmic sessions of most devices. A reduction of gate resistance by A, adding contacts to both sides, or B, folding. Thank you.